In this lesson, we're going to focus on estimating a population proportion using confidence intervals. In the previous two lessons, we talked about estimating a population mean. So let's do a quick review of those before we move on to population proportions. So when you're estimating a population mean, and you know what the population standard deviation is, then we're going to use these to find our critical values. Then we can use the critical value to find our error. Okay, and our error is going to be our z critical times our population standard deviation over the square root of n, where n is our sample size. Our point estimate is x bar, which is our sample mean, and that's what we're going to use to add and subtract the error in order to create our confidence interval. So when we get our confidence interval, we're going to take our point estimate, which is our sample mean, and subtract our error. That's to get our lower limit. And then to get our upper limit of the confidence interval, then I would add my error. And then the last thing that we talked about, if we need to figure out what sample size we need, if we want a specific confidence level and a specific margin of error, we can use this formula, n equals z critical squared times our population standard deviation squared over our error squared, and that will give us our sample size when we're looking for a specific level of confidence in a specific margin of error. Oh, and let me put over here, when we use the calculator function to find our confidence interval, that would be z interval. Okay, then we went into discussing, well, what do we do if we don't know what sigma is? What if we don't know what the population standard deviation is? And we want to estimate a population mean. The idea is still the same, but we're going to use a different distribution. This is when we do not know sigma. And that's typically the case in the real world. It's very rare that you would actually know the population standard deviation. So when you don't know the population standard deviation, you use t's to find the critical values. And then our error is going to just be t critical times our sample standard deviation, because when you're using the t distribution, you can use the sample standard deviation to estimate the population standard deviation. And then we divide by the square root of n. Our point estimate is still going to be x bar because we're still trying to estimate the mean. So we want to take our sample mean and add and subtract the error. So our point estimate is still x bar. To find our confidence interval, we just take our x bar, which is our point estimate, we subtract our error, and then we add our error so that we can get our interval. And then, of course, we have the calculator function. We would use t interval. So now let's talk about population proportions. And sometimes when you're trying to find a population proportion, what you're doing is you're dealing with qualitative data and you're looking at the number of successes out of the total. This is called your proportion. When you're looking at the population proportion, okay, that notation is P, but when you're looking at it as the sample proportion, we use the symbols P with a little dash up where the exponent would be, and that's called P prime. And sometimes you'll see it like this, where it has like a little arrow above the P, and that's called P hat. Our book uses the prime notation, so that's what I'm going to try to remember to stick with. However, if you see the P hat, it means the same thing. It's your sample proportion. So we're going to create confidence intervals for population proportions the same way we did before, where we use a point estimate, and then we're going to add and subtract the error to get our interval. Well, when we're dealing with proportions, we're going to use the sample proportion as our point estimate, and then we add and subtract the error. Now, the error, when you're dealing with the number of successes and we're talking about a binomial distribution, if you think back to section 4.3, let me make a note of this over here. Your standard deviation is going to be the square root of n times p times q. And remember, q is the probability of failure, where p is your probability of success. And then in this case, because we're talking about using the sample proportion, we're going to stick that prime in there. But it's the same thing. We're finding the probability of success, which is your proportion, that's your P, and then the complement to that would be your Q. So if P prime was, say, for example, 60% or 0.60, then Q would be 0.40, because you want them to add up to 1. And then, so let me write that down too as a reminder that Q is the complement of P. Okay, now if you recall also thinking back to section 4.3 with binomial distributions, the mean is going to be your n times your P. So just a quick refresher. Now, to find our error, we need a critical value. When we are using proportions and we're dealing with the binomial distribution, we can use these to estimate our critical values if, so let me make a note down here, if n times p is greater than 5 and n times q is greater than 5. If this is the case, then we can use these to estimate binomial distribution. Now, in order to find our error, we're going to use z critical times the square root of p prime times q prime over n. Now, that n is included under the square root, so be careful not to write it like this. Because I see students make this mistake all the time. That n is included in the square root. So just a quick note I wanted to add in there to show you a common error. Okay, now, we can only use z critical if we have the case that our sample size times our p prime is greater than 5, and our sample size times our q prime is greater than 5. That's the only way we can use z critical. The sample size needs to be big enough for us to be able to estimate the binomial distribution with the normal distribution. So you always want to check to make sure that you can do that. Okay, and then the last thing I want to mention is that on the calculator, the function that we're going to use is 1 prop z-interval. Okay, so when we're using z's to estimate proportions, and we want to find that confidence interval, this is what we're going to use on the calculator. So in the first example, it says, suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 responded yes. We're going to use a 95% confidence level, and we're going to find a confidence interval to estimate the proportion of adult residents of the city who have a cell phone. So one of the things you really want to look at when you're doing confidence intervals is you want to identify what the parameter is that you're trying to estimate. Okay, so far we've talked about means, and now we're talking about proportions. So we have to narrow it down to what formula or what calculator function we're going to use based on what they're asking us. They are asking us not about the mean or the average of a sample or a population. They're talking about proportions of the population and of samples. So that means we're looking at P's now. Okay, so when we're dealing with proportions, we have certain formulas. We have, when we're doing it by hand, we have our error formula that is z critical times the square root of p prime times q prime over n. And then if we're using the calculator, you want to use 1 prop z-interval. Now, but in order to be able to use that z-critical, we need to make sure that our sample size is big enough. And if you recall, we want to see if n times p prime is greater than 5. We also want to check that n times q prime is greater than 5. Now, if we look in this example, we have that the sample size is 500. So now we have to identify our P and our Q to put in here to check to see if that's greater than 5. So our P, or our P prime, is the success from the sample. All right, so when we look at this, it says we have 500 people surveyed. We're interested in the number of people that have cell phones, and in here it says 421 responded yes. So for our sample proportion, or our P prime, we're going to have 421 out of 500. And when we put that in on the calculator and we get a decimal value, that's going to be 0.842. So the complement of that will be our Q prime. And when I take 1 minus 0.842, that's going to give me 0.158. So here's our Q prime and here's our P prime. Now when I take 500 times 0.842 and I take 500 times 0.158, those are definitely bigger than 5. So this tells us that I can use z critical. I can use the normal distribution for my critical value. Okay, so to figure out our critical value, we know we're using a 95% confidence interval. So I know 95 is going to be in the middle, which means 2.5% is going to be on either side. So to find my z critical, my values of z's here, I'm not concerned about the negative or the positive. I'm just looking at how far away from the center I am. I'm going to do inverse norm, 0.025. 0 is my mean, 1 is my standard deviation. And I'm going to get, let's see, 1.96. It's going to give me actually negative 1.96, but we're actually not worried about the negative. We really want to just see how far away from the mean we are. So I can label this as negative 1.96, but when I write down what my z critical value is, it's going to be positive 1.96. Okay, so now I can use my formula to find my error. So my error is going to be my z critical, which is 1.96. I'm going to multiply it by the square root of my p prime times my q prime, all divided by 500, and then I take the square root at the last step. Remember that that 500 is under the square root. When we do that, we get 0.032. So now to find my confidence interval, I'm going to take my point estimate, my p prime, and I'm going to add and subtract my error. So I'm going to get, when I take 0.842, I'm going to subtract my error, and that's going to give me the low end of my interval, and then I'm going to take 0.842 and add 0.032. That's going to give me the high end of my interval. And that's going to give me 0.81. And then on the high end, we're going to get 0.874. Now my interpretation. I would say something like, we are 95% confident that the true proportion of people in the city that has a cell phone is between 0.81 and 0.874. Okay, now let me show you how we do this on the calculator. It's pretty much the same method. I just want to make sure that I go through it with you. And again, on the calculator for this, we're going to use one prop z interval. So let me pull up my calculator. So to access the confidence interval functions on the calculator, we're going to do it just like we did before. We're going to go to the stat option, and then we're going to come across the top and go to tests. In this case, since we're doing the one prop z interval, I'm going to scroll down and look for that. That's this right here, option A, one prop z interval. I'm going to hit enter, and there's a few things that I need to put in here. X in this notation here on the calculator is the number of successes. So in this problem, it tells us that there were 421 that responded yes. So that's going to be our number of successes. And then our sample size was 500. And the calculator will find the value of P for you by taking X divided by N. Then we're going to find, or then we're going to put in our confidence level, which was 0.95, and then we're going to put in calculate. Okay, so it finds, the calculator uses the notation p hat. That's the same as our p prime. And so that's our probability of success, that what we got when we did it by hand. And then up here, of course, it gives us our confidence interval. Our lower value that the calculator gives us is 0.81003. And then our upper value is 0.87397. When we did it by hand, we got 0.81 and 0.874. So the calculator goes out a little bit further for us, but it's pretty darn close. So that's how you do your one prop z interval on the calculator. In the next example, it says, for a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So this isn't asking for means, this is asking for a percentage, which is another way to say proportion. And so we're going to use P's. That's going to be our point estimate. Success is going to be the people who are registered voters. So in this case, we have 300 out of 500 that are registered voters. When we put that in terms of a decimal, that's 0.6. So that means our Q prime is going to be 0.4. Now, in order to use that error formula with Z critical, I need to make sure that the sample size is big enough. So I want to make sure that my sample size times my P prime is greater than 5, and that my sample size times Q prime is greater than 5. And that definitely is true. So we can use the normal distribution and our Z criticals for this. So to find my critical values, I'm looking at a 90% confidence interval. I want to figure out how far away I am from the mean, which means each of these wings is going to have to be 5% so that the whole thing adds up to 100. And so I'm going to use inverse norm. I'm going to put in 0.0501. And that is going to give me negative 1.645. So my Z critical is going to be 1.645. So to find my error, I'm going to take my Z critical, which is 1.645, times the square root of my P prime, which is 0.6, times my Q prime, which is 0.4, divided by my sample size, which is 500. Okay, let's see. When we do this, we get an error of 0.036. So I'm going to take my P prime and I'm going to add and subtract my error to come up with my confidence interval. So when I take 0.6 minus 0.036, that's going to give me my lower limit. When I take 0.6 and I add 0.036, that's going to give me my upper limit. So that'll give me 0.564 for my lower limit, and for my upper limit, 0.636. Now for my interpretation, I would say something like, we estimate with 90% confidence that the true proportion of students registered to vote is between 0.564 and 0.636. Okay, let's practice this on the calculator. So we're going to use 1 prop Z interval. To get back to that menu, we're going to hit the Stat button, and we're going to arrow over to Tests, and then I'm going to scroll down and look for 1 prop Z interval. Now be careful not to hit the 2 prop. It's right underneath it. We're going to get to that in the next chapter, but we're finding the proportion of 1 population, so we want to make sure that we're using this one. I'm going to hit enter, Now, X is the number of successes. In this case, it was 300. Our sample size was the same, so I'll leave that as 500. And in this case, we were doing a confidence level of 0.90, and then I'm going to hit calculate. So here's my confidence, my lower and my upper limit, and it's giving us that our p hat, or our p prime, is 0.6, which we calculated by hand. And then it gives us our sample size. It lists it here. We got, when we did it by hand, 0.654. This was rounded to 3 places. Same thing here. We got 0.636. So this rounded to 3 places here as well. So the calculator went out a little bit further than we did. Last example before we go on to the mixed review. We have, suppose a mobile phone company wants to determine the current percentage of customers aged 50 and up who uses text messaging on their cell phones. How many customers aged 50 and up should the company survey in order to be 90% confident that the estimated proportion is within 3 percentage points of the true population proportion? Okay, so that's a lot of information given to you. And we know that this is talking about a company that wants to survey how many people that, and find out how many people are using text messaging in the older generation. But when we circle back around, we read it through again, the question's actually asking how many customers should we have if we want to be 90% confident and we want to be within 3 percentage points. What the question is asking us about is sample size. What should the sample size be in order for us to be 90% confident and within 3 percentage points? So our confidence level is going to be 0.90. Our, our error is going to be plus or minus 3 percentage points. But when we use our calculations, we want to write it as a decimal. And our sample size formula for proportions is going to be 1/4. You're going to take your z critical and you're going to square it. And then you're going to divide it by your error squared. Okay, now I'm going to let you guys find the z critical yourself and check it. You want to make sure that you are 90% confident. So you want to see how far away in terms of standard deviation are you from the mean. So that's going to be your job. So pause the video for a second and practice doing that. And then unpause and see if you can get it. Okay, so you should have gotten that your z critical is 1.645. Now putting that in our formula, we have 1/4 times 1.645 squared over our error squared, so that's 0.03 squared. You would get 751.7. Now, when you're dealing with sample size, even if this number here is less than a 5, you always want to round up because you want to make sure that your sample size is big enough so that this works. So always round up. Now, if we actually knew what the value of p prime was, then we want to use this formula to find the sample size, where we take z critical and square it. Then we multiply by p prime, q prime, and we divide by the error squared. So we use this formula if we do know the value of p prime and q prime. Otherwise, if we don't know, we use this formula. So let me make a note of that. If we don't know p prime, we use this formula. Then if we do know p prime, then we use this formula here. Okay, now we're going to start the mixed review, and what I really want to focus on when we're going through these mixed problems is I really want to focus on reading the problem carefully and making sure that we can pick out the key information so we can determine which method that we're going to use. So question 1 says 108 Americans were surveyed to determine the number of hours they spend watching television each month. It was revealed that they watched an average of 151 hours each month with a standard deviation of 32 hours. Assume that the underlying population distribution is normal. We're going to construct a 99% confidence interval for the population mean hours spent watching television per month. So we're going to find the confidence interval. I'm not going to worry about sketching the graph because we're going to use the calculator. And then we're going to calculate the error. We are talking about averages, not proportions here. So when we look at the average, it talks about 108 people that were surveyed. So the sample size is 108. It says from the sample, they found an average of 151 hours. So that means our X bar, our sample mean, is 151 hours. And the standard deviation from the sample is given as 32 hours. If you go on to read the rest of the problem, it never gives us any information about the population standard deviation. We don't know what that is. So when we do not know what the population standard deviation is and we're trying to estimate the population mean, we use the t-distribution. Now, using the calculator function, we need to use t-interval, and we need to put that information on the calculator. We would put in X bar, the sample standard deviation, and our sample size, and put that in under t-interval, and what we would get is 142.92, and we would get 159.08 as our upper bound. So here's our lower bound, here's our upper bound. Now, if I were to interpret this, I would say that we are 99% confident. Oh yeah, let me write that down too. Our confidence level is 0.99. We would say we were 99% confident that the true population mean hours spent watching TV per month is going to lie between 142.92 and 159.08 hours. So that's how we want to interpret this. Now, the other thing that we wanted to do is figure out the error. We're going to practice doing that. Remember that the mean is in the center, and we add and subtract the error to get our upper and our lower bounds. Our mean is in the middle, 151. My lower bound is 142.92. My upper bound is 159.08. So I want to find the error. What am I adding and subtracting to 151 to get 142.92 and 159.08? Well, when I find this difference, I'm going to find that the error is 8.08. And I can do that by taking 151 and subtracting 142.92. Or I can take 159.08 and subtract 151. Either way, we should get the error is 8.08. Next example says a sample of 20 heads of lettuce was selected. Assume that the population distribution of a head weight is normal. The weight of each head of lettuce was then recorded. The mean weight was 2.2 pounds with a standard deviation of 0.1 pounds. The population standard deviation is known to be 0.2 pounds. Construct a 90% confidence interval for the population mean weight of the heads of lettuce. We're going to state the confidence interval. I'm not going to worry about sketching the graph, and we're going to calculate the error. Okay, so we have a sample of 20 eggs, so our N is 20. The sample information is given to us as the mean of the sample, so that's our X bar, is 2.2 pounds, and the standard deviation of the sample is 0.1. Then it goes on to say that the population standard deviation is known to be 0.2. So we're estimating the mean, and we know what the population standard deviation is. So that means we're going to use z-interval. Okay, now when we put all the information in on the calculator using z-interval, you should get that your confidence interval is 2.1264 for your lower limit. And then for your upper limit, you should get 2.2736. Now, I know my X bar is in the center. And then I'm going to add and subtract to get my upper and my lower bound of my interval. So to see what that error is, I can I can subtract and figure out what that difference is, and we would get that the error is 0.07. Now, just to make a point of this, we're using the z-interval because we're estimating the mean, and we know the population standard deviation. That's why we're using the z-interval. In example 3, it says, suppose the marketing company did a survey. They randomly surveyed 200 households and found that in 120 of them, the women made the majority of the purchasing decisions. We are interested in the population proportion of households where women make the majority of the purchasing decisions. We're going to construct a 95% confidence interval for the population proportion of households in which the women make the majority of the purchasing decisions. It says, state the confidence interval, sketch the graph, calculate the error bound. Okay, so in this question, if we carefully read it, it gives us our sample size is 200. The number of successes, because we're interested in the women that made the majority of the purchasing decisions. Our P prime is going to be 120 out of 200. How did I know we're going to use our P's? Because several places in the question, it's asking about the population proportion. So that's how I know I'm going to use P primes. Now, to find our Q prime, I'm going to take 120 minus, or 120 from 200 to get that difference. That's going to be 80 over 200. Okay, now that's going to give us our P prime and our Q prime. So we're going to use one prop Z interval. We should make sure that our N times P prime is greater than 5 and our N times Q prime is greater than 5 to make sure that we can use our Z criticals here. So if I take 200 times my P prime, that's 120 over 200. If I cross off my 200s, I get 120, and 120 is certainly greater than 5. Now, if I take 200 times Q prime, that's 80 over 200. If I cross off my 200s, I get that 80 is greater than 5, and that works as well. So it's totally okay for us to use that. Now, when I put that information in on the calculator, I'm going to put that X is 120, My sample size is 200, and I'm going to get that I have a confidence interval of 0.5321 to 0.6679. Now, to sketch the graph, just because we haven't done it yet, I've kind of skipped that part. Whoops, that doesn't look very good. My point estimate is my P prime. So that's 120 over 200. And when I divide that, I'm going to get 0.6. So that's my P prime that we're estimating in the center. Now, my interval was 95%. So I'm going to have 95% in the middle. So when I form my interval, that means on either side, my low end is going to be 0.5321. And on my high end, I'm going to have 0.6679. So there's just a quick sketch of the graph. Since we haven't done that yet, it's good to practice. Now to find the error, I need to figure out what that difference is. What am I adding and subtracting to 0.6 to get my ends of my intervals? Well, when we do that arithmetic, and I take the difference between 0.6 and 0.5321, I'm going to get the error is 0.0679. In number 4, it says, a poll of 1,200 voters asked what the most significant issue was in the upcoming election. There was 65% that answered the economy. We are interested in the population proportion of voters who feel the economy is the most important. Construct a 90% confidence interval, and then we're going to state the confidence interval in the error bound. So our confidence level is going to be 0.90. Our sample size is 1,200. And if you read carefully, we're interested in the population proportion. So we're going to use P's. Now, they didn't tell us out of the 1,200 how many actually answered the economy, but they told us the percentage, which is our proportion. So our P prime for the sample is 0.65. So because we're dealing with proportions here, I want to use one prop Z interval. Let's make sure that our conditions hold so that we can actually use this. So we got to find n times p prime is greater than 5, and we've got to find if n times q prime is greater than 5. So our n is 1,200. If we take 1,200 times 0.65, that's definitely greater than 5. And if we take 1,200 times q prime is 0.35, because that is the complement of 0.65. When we take that, that's definitely greater than 5. So this definitely works. So we can use the one prop Z interval. Now, when we do that, we need to put in our x's, which is the number of successes. They don't directly tell us that in here. They tell us that 65% was the proportion, and we know the total is 1,200, so we can figure out the number of successes by finding 65% of 1,200. So if I take 0.65 times 1,200, that's going to give me 780. So when I plug this in on the calculator, I'm going to put in x, which is the number of successes, is 780. I'm going to put in my n, I'm going to put in my confidence level, and then what I'm going to get is my confidence interval is going to be 0.62735 to 0.67265. That's our confidence interval. Now we know that the center is our value of P, our 0.65. That's our point estimate. when we figure out the difference between our two n values, so we're going to take 0.6 minus 0.62735, or I could do 0.7265 minus 0.6. Either way, we're going to get the error is 0.02265. Okay, and the last example for the mixed review. Among various ethnic groups, the standard deviation of heights is known to be approximately 3 inches. We wish to construct a 95% confidence interval for the mean height of male Swedes. 48 male Swedes are surveyed. The sample mean is 71 inches. The sample standard deviation is 2.8 inches. So we need to find the 95% confidence interval. So our confidence level is going to be 0.95. Our sample size is 48. I got that from right here. We're estimating the mean height. When I look at that, I'm doing a confidence interval for the mean height. So we're estimating the mean. Now it says the sample mean, that's our x bar, is given as 71 inches. It says our sample standard deviation is 2.8 inches. And then at the very beginning, it tells us what the population standard deviation is. And it says that's 3 inches. Because we're trying to estimate the mean and we know our population standard deviation, we're going to use z-interval. So we're going to put all that information in on the calculator, and we're going to get that the interval is 70.151 to 71.85. So that's our confidence interval. If we draw a picture, I only did this one other time, so it's good to practice. Our mean for our sample is our point estimate. That's going to go in the middle. We want a 95% confidence interval. So 95% is going to be in the middle. And then we found that our confidence interval, our lower bound is 70.151 and our upper bound is 71.85. So that's what our picture looks like. Now, if we want to find what our error is, we need to figure out what that distance is from the mean. So I'm just going to find that difference, and when I subtract, I'm going to get 0.849 for my error. So to sum up real quick, if we're estimating means, we want to use either z-interval or t-interval, depending on if we do or we don't know the population standard deviation. If we do know the population standard deviation, then we're going to use z-interval. If we don't know it, we're going to use t-interval. If we're doing proportions, we want to make sure that the conditions are correct, that we have a large enough sample size, and then we can use the one prop z-interval, where we use z-criticals, because we're using the normal distribution to estimate the binomial distribution. So we want to make sure that that n times p prime and our n times q prime are both greater than 5 in order for that sample size to be big enough to be able to use that method.